Thank you, everybody. Maybe we'll get a few more people in. They've probably just gone for a quick break. Welcome back, or welcome to the most interesting, cool, and let's face it, sexiest track at State of Open, Con23. So my name is Mike Bursell, and I'll get on to what I do a bit later on. But I'm here to talk to you about confidential computing. So let's first start off with understanding what the problem that we're trying to solve here, and what's the issue that is at stake. But we'll start off with a story, because I like stories, and I think stories are always good, and we don't always use enough of them in security. So let's start with a story. Once upon a time, computing was simple, and computing was safe. And it was mainly run by people like this, mainly actually run by women making things just work, and you didn't need to worry about security particularly. Unless, of course, you were trying to do cryptanalysis on a foreign power, but that's a kind of different type of security, right? Then along came the Brits, who messed it up royally. What do? Well, it comes down to tea and cake. So the older among you may just about remember Lyons tea shops. Does anyone remember Lyons tea shops? It's just me, isn't it? They were everywhere. They're in all towns all across the UK, and they did tea and they did cake as well, which is good. And you could go along, and it's kind of like Costa, but really not. But kind of think that, right? Costa, Starbucks, whatever. But they were so big that they needed to think about how they managed their distribution. And some bright spark thought, these computer things, couldn't we use them? And said, oh, God, let's give it a go. And, they had a couple of spare rooms and, lots of heating they didn't know what to do with. So they created what's called Leo 3. Obviously, Leo 3 is the third one. This isn't a pope. This is Leo 3, the computer, okay? And this is a picture of, I think, the data entry of Leo. They obviously had the men in the foreground and the women in the background, because it's safest that way, But this is what it looked like. And the evil geniuses who were working on Leo came up with a clever idea, which is called multitasking. Okay? Now, multitasking sounds like a great thing, because it means that if you're not using all of your compute power all the time, someone else can use it, or a different batch job or whatever could be using it at the same time. And ever since, in computing, people have been obsessed with sharing. This is not a good thing. Not only for computer security, but also for cake. I'm not a big fan of sharing cake, as some of you may have realized, but it creates all sorts of problems. So let's talk about why it creates problems, okay? The problem is basically computers. Because, well, it's not really, it's kind of actually the workloads rather than computers, it's how they work. So I'm going to move us forward a few decades now, not quite centuries, a few decades, to talk about standard virtualization. So I kind of assume that most people here have heard of virtual machines, have heard of containers, have heard of all those sorts of things, right? So the way that they work is you've got these kind of workload things, applications, whatever it may be, running on a host operating system in some hardware. That's kind of computing, right? And the problem is that these workloads may be from different users, or one of them might get compromised, or completely different tenants. And you want to worry about how you isolate these workloads, which are running at the same time, from each other. And one way of thinking about isolation is called the CIA triad. I can say those three letters here because I'm talking about confidentiality, integrity, and availability. Okay? So confidentiality is stopping one workload looking into another workload, right? That seems like a good thing. Integrity is about one workload stopping the other workload, basically being able to mess with the bits and the bytes and change the data or even the program inside another workload. Availability is making sure that one workload can't stop the general working of the networking or the storage or just the general CPU usage of another workload. And generally availability, you can tell if your workload is not doing anything, it's not responding, it's not too difficult. which is a great start. So we're kind of going to worry mainly here about the other two. So there's 3 types of isolation for workloads. One is workload from workload isolation, right? This is what I talked about just now, and that is stopping one workload looking into or messing with another workload. And it turns out that we're quite good at this. It's not so hard. We've had 20, 30 years of work, or maybe more, depending on how you look at these things, of working out how to stop these things. And VMs, containers, do this pretty well. The second is actually when you start talking about the host, because you want to stop your workload from messing with the host. Because if this workload can mess with the host and change what the host is doing, then they can do whatever they want to the host or, in fact, to any other workloads, right? And it turns out, again, that VMs and containers are pretty good at this. Hypervisors, all those bits and pieces, right? VTX extensions, blah, 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 and all the nice things that containers do with groups. There is a third type, and that is workload from host isolation. This is where things kind of get interesting and worrying. And the problem is basically that the model we started off the world was that whoever owned the hardware was the person who's going to be running the applications. But if you're putting stuff in the cloud, then the person who's actually running the application is someone completely different. It's not Amazon or Microsoft or IBM or Oracle or whoever it is who's actually running the applications. It's their tenants, it's their customers, right? And the problem is that classical virtualization techniques can't deal with this problem. They're not designed to. The way they work is basically they expect to be able to look into the memory pages on the machine and do anything what they want with them. Which means that if you own the host, you own the workload. And by own, I mean own with an O or with a P. So if you compromised it, it works either way around. So let's talk specifically about the edge. So this is obviously a little bit awkward, right? Because if you can't be sure you entirely trust your cloud or your edge provider, it's going to be good. But of course it's okay. Of course it's okay if you trust your CSP and all of their sysadmins and all of the hardware, software, and the firmware stack from compromise of the supply chain or at runtime now and in the future. And if your entire CFO and board and the auditor and the regulator do as well. And if you're running sensitive data or have customer information or you've got sensitive algorithms or you work in finance or defense or healthcare or pharma or you have cryptographic keys or any of these things, you need to start worrying about this sort of thing. And the regulators are worrying about this sort of thing. Not all clouds are good, sorry. So, we've got a problem. How do we address it? So, there is something called confidential computing. And this is a definition from the Confidential Computing Consortium, which is of whom we have our beloved leader, Steve Wally, actually here in the audience today. And confidential computing is the protection of data in use, so not just in transport or in storage, rest, by performing computation in a tested, hardware-based, trusted execution environment. Lots of words there. The key thing to be aware of to start with is it's hardware-based. So it is hardware, CPUs, which are providing you with the protection. And we'll come back to that in a bit. So the CCC, the Confidential Computing Consortium, not the Chaos Computing Club, is a Linux Foundation project. It's focused on open source software, as it should be, and it has broad industry adoption. There are lots of big names there of whom you will have heard, as well as lots of startups as well who are involved with it. And it kind of looks at the world a bit like this, right? If you think about privacy-preserving computation, or something called PETs, privacy-enhancing technologies, trusted execution environments sort of sit here, and confidential computing is hardware-based trusted execution environments for full general compute. So things like TPMs don't count because you can't write a general application and run it in in a TE, right? You can't write something in Rust or C or whatever and run it in a TPM. Whereas you can using these technologies. So the technologies which are best known, Intel's SGX, AMD's SEV SNP, ARM's CCA Realms, coming out in ARM 9 about now. Intel recently announced TDX, and absolutely not AWS Nitro. AWS Nitro does not meet the definition of confidential computing as per the Confidential Computing Consortium, because it's not protected all the way down to the hardware. I'm not going to go on about that, but it just doesn't. So let's talk about how it does this, okay? So it uses what are called trusted execution environments, and they're based in the CPUs. And what they do is they encrypt workloads. Specifically, they encrypt the RAM, the memory pages of workloads. And each workload has a different cryptographic key, which is kept in the CPU. And that data page is memory page is only ever decrypted when it's actually in the CPU. And it's then re-encrypted immediately before going out into general RAM. And so they can protect integrity and confidentiality, but they can't really protect availability, because if you have control of the CPU or something like the operating system, you can stop applications having access to CPU resources, networking resources, whatever. Not much you can do about that. So confidential computing is about deploying applications, workloads to TEs, to trusted execution environments, which is harder than you might think. But first, is it really T? Remember I started off with a T metaphor? I'm going to go back there because I'm a Brit and I'm actually giving this in the UK for a change. I don't often get a chance, so I'm going to go with it. Just stick with it. It's cool. There'll be cake too. So here is a scenario. Like, let's pretend, and you don't need to pretend very hard, that I love tea and cake. Okay? So let's say I've got some cake and I want to eat it with some tea. I call your cafe and to order a pot of tea, okay? And you'll provide the pot of tea, and I'll come with the cake. But before I turn up, I can't check whether you've provided me with real tea. And by real tea, I mean proper tea, not any of your herbal rubbish, okay? I mean proper tea, Assam, something like that, okay? Earl Grey, okay, not really my thing. Ceylon, anyway, that's what I'm looking for. What if you do the very worst thing, which is provide a pot of coffee instead of tea? How am I supposed to know what to do? So, what I need is a remote, trusted tea taster who can warn me before I turn up with my cake, which is the application, the workload, in case you haven't got there yet, right? Whether I should turn up or not. So this is it. So either my trusted tea tester, she will say, that's lovely tea, or she'll say, no, don't, whatever you do, turn up. Okay. So here, to sort of pull the analogy together a bit, and I mean a bit, I know I'm pushing it, the CSP's machine is basically the cafe that I'm going to. The T is a trusted execution environment, and I'm really sorry about that. The coffee would be a spoofed TE. Right? So someone pretending, the CSP saying, of course I provide you with a real tea, you can trust it, it'll be fine, but actually they haven't. And the cake is my workload and the data. Yeah. So, attestation, and we saw in that definition, it said an attested hardware environment. I didn't push it, but this is the important thing, really, really important. Attestation is the measurement of the T instance by a trusted entity and the subsequent verification of it. Okay? So either valid, it's okay to send your application, or it's a spoof, don't deploy it. So the question is, how do you find a trusted entity in the CSP, which owns everything, including the hardware, and the software, and the OS, etc., etc.? It's really difficult. But the CPUs we're using thought of this, or the creators did, and they created the capability for CPUs to do the measurement and to sign the measurement cryptographically, so you've got something to check. Okay? So they'll sign the TE and its memory pages, which means that you've got a chance of checking what's going on. So actually, and this is where it gets we have to break the analogy bit. The measurement is on the host cafe, but the validation must be managed by a trusted entity who is not owned, not controlled by the CSP, an attestation service. Okay? And so we've got two very trustworthy looking people. I know they're trustworthy because they're wearing white lab coats, and they've got a thing of blue liquid, so they can certainly be trusted. And they will tell me whether or not it's okay. And if it is, I'll bring the cakes. Now, the problem is this is very, very difficult to get right because attestation is very complex. And of course, all of the providers of the CPUs provide completely different ways of doing it. Why wouldn't they? But also, it's devastating if you do it wrong, because if you think you've got a good measurement, but you haven't, you've just given away everything that you're trying to protect in the first place. So enough with the tea and cake. Let's talk about an attestation process. This is the safest way of doing it. There are other ways. This is the safest way. So let's say the green box is a trusted execution environment that I want to set up and I want to deploy something to. We've got a CPU, and off the box, off the CSP, we've got an attestation service, and we've got a user who's looking very chipper this morning. I don't know. She probably had some very nice tea. So the TE creates itself, or is created, and we say, please measure it. And the CPU does measure it. You can tell it's a measurement because it's in zeros and ones. Obviously, low-level stuff, so it must be zeros and ones. Binary, ladies and gentlemen. And it signs it. It's got a little padlock again. It must be nice and safe. And it sends that to the attestation services, which are the nice people in the white coats with the blue liquid. Now, if that is good, it's checked it, it knows it's got a list of known good measurements, it will then say to the user, it's fine, you can deploy your application. You deploy it, you run, you're happy. Now, of course, it is possible to deploy the application first, but if you do that and it's spoofed and there's anything sensitive in your application, you've just lost that as well. So this is the safer way of doing it. Okay, so we'll just wrap up, because I want to leave a little bit of time for some questions. Who needs confidential computing? It's everyone, okay? Just so I don't want too much peril and excitement in this. Healthcare, finance, pharma, defense, all of those people, they need it, because they deal with sensitive data, they deal with customer data, they deal with citizens' data, etc., etc. In fact, anyone with sensitive data or sensitive algorithms. Because if you are running on a complex risk analysis process for a bank, that's often worth more than the actual data you're taking in the first place. So you want to be protecting that. So it might be in the public cloud, or it might be in the edge, or even in your private cloud if you're worried about insider threats. So, yep, everyone needs it. So I'm sure you have nice parrots like that in Brazil, don't you? Yes, you do. Okay, fine. We've got Nick from Brazil. He's approved this slide. So, very quickly, why open source? You may have noticed we're at a big open source conference. Well, the first thing is it's visible. You need to know what you're running. Because if you're going to trust your crown jewels, your most sensitive data and applications to the cloud or to a project, you want it to be open source. You want it to be auditable. And, our view is that everything should be open source. It should be the meetings, the chat, and just a slight plug here. NARCS is an open source project, part of the Confidential Computer Consortium. Nick's wearing a T-shirt. You can have a look at it, have a play with it. Design process, everything we think should be open source. Because if it's not open source, you can have no technical assurances in the code, nor any basis to trust any system using it. If you're interested in trust, I have a book out, obviously plugging it, but yeah, search my name, you'll find it. So this is it. This is the talk. I am Mike Bursell. I was until 5 p.m. on Monday the CEO of Profion, a confidential computing consortium startup. I made myself redundant on Monday because people don't get it yet. We're about 12 months off for the sort of the sort of adoption we need. So we had to close down the company very sadly. If you're looking to hire people who know about this sort of stuff, I'm looking, as are all of my staff. But this is really cool, really interesting stuff, and you should get involved. Love to talk to you about it. Contact me on LinkedIn. We've got 9 minutes for questions. Gentleman over there with a question. He has a mic.
Thank you. That was a really interesting talk. It's an area I don't know much about. I've got a silly question and a sensible one. Do you want the silly one first?
I'm going to say there are no silly questions. There are silly questions. Give me that one first.
Okay. Why did your tea taster have a coffee cup in front of her? She's dodgy.
Because you can't be sure.
Yeah. You get yourself a better tea tester. I'm still trying to wrap my head around when and where you might start using this, because if I was concerned about the integrity of the CPU that I was running on, I'd also be concerned about the integrity of my database, the data in transit to move to the cloud. I guess being a pragmatist at the moment, I might be incentivized to keep that data closer to the business, either in a data center or the old-fashioned server room inside your own premises.
Yeah. And that's
what would you say to people who are considering that?
I think the problem is mainly in the other direction. People are moving stuff out without realizing the dangers of it to the cloud and to the edge. That's changing. When it comes down to it, you have to trust something. You have to have, in fact, there's 3 things you need to trust in the model I've talked about. One is you have to trust the CPU, and that it's come from, let's say, Intel or AMD or ARM. And you have to, you need to trust them, but you need to trust that it's come from them. So trusting that it's come from them is dealt with by the certificate chain when you do the measurement. Okay? You then have to trust them, and when it comes down to it, something's going to be running your code anyway, right? So there's it. You have to. The second thing you need to trust in this model is our code, which is basically the runtime which runs inside it and makes it all happen and does the attestation. Okay? The third thing is your application. You wrote it or you bought it, you kind of got to trust it. Nothing else should you need to trust. The host OS, the hypervisor, the admin, any libraries, any of that stuff, any other workloads. So
what about the storage, though? Most enterprise applications have a big
the answer
database.
to that is you should make sure that anything that comes out of there is encrypted. And the NARC's approach, transparency encrypts all network traffic. Storage isn't supported yet, but absolutely you have to do that as well. You should always do that all the time.
So the general principle is that when the data comes into the CPU, that's probably the only place where it has to be unencrypted to perform the work.
Yeah.
Now I get it. Thank you.
We have another question. Thank you. Good questions.
What's the performance overhead from the encrypting the memory page?
Yeah, sure. So not so bad. It depends enormously on a couple of factors, really. Well, 3. One is the architecture. So Intel SGX versus Intel TDX, which is coming, versus AMD. Generally, for most workloads, you're probably talking single-figure percentage points, maybe low double figure from that. Another thing is you've got a runtime in that's going to be running things, right? Typically, that'll add something. The NARC's project uses WebAssembly, which is heavily jittered and improving nicely. So again, you're not talking more than a few percentage points. There's also the case that you can write pathological applications, which are going to make this very bad, because for instance, typically you're going to do a lot of entering and exiting, and that's very expensive because you've got a lot of syscalls and all the context switching, basically. So you can write pathological ones, but on the whole, it's considered worth it, I think. We have, I think, 2 more questions, one at the front. And
I borrowed the microphone, sorry.
No?
Is the enclave, is it big enough to fit the entire VM in, or do you have to simply keep some of your data inside the VM, inside the enclave?
Okay, so this is not a VM play, okay? So the way that some of the chips implement it is by doing a VM. But by a VM, all we mean is a vCPU and some memory pages. Now, if you want to load an entire Linux virtual machine in there, knock yourself out and deal with the TCB yourself. That's not the approach the NARC's project takes. For instance, provide a WebAssembly runtime which is under 15 meg. Okay, so you don't be. But the answer is yes, you can scale up to gigabytes with some of these technologies now. Any other? I think you had a question, did you? Yeah. Yes. Sorry. And please find me afterwards and do the LinkedIn thing. Mike Bursell, you'll find me. There's only not very many of us.
Is it possible to, so I'm quite interested in the idea of like compute over data, so sending the algorithm to the data. Is there a way to do that in like a trusted way? So for example, if you want to run compute on multiple different confidential computing servers that hold health data and then aggregate those results into a larger sort of...
Yeah, sure. So, I mean, there are companies, startups and larger companies, who are creating frameworks that do that to allow you to do that. Or you can just run a standard, the TEs are very well suited to microservices. So if you have a microservice-based architecture, just design a microservices architecture and move things around as you otherwise would. As we already said, you should be encrypting stuff between them anyway. And if you, again, the way that NARCS does it, you have a certificate which is based in a particular application instance, and you can use that to help yourself out. But yes, absolutely you can. You don't need to put it all in one place. You can use this stuff for generalized compute. Write your current microservices. As I said, NARCS uses WebAssembly, so you can write stuff in Rust, C, C++, Java, Python, Go, compile it to WebAssembly, and then just run it as you'd expect. I think we've got one here first, and then you. We've got a couple more minutes, and then I will be around for a while. Please do find me. And anyone online, waving at the camera, Mike Bursell on LinkedIn. Look, the cameraman's waving back. Oh, that's really sweet. Please do that.
Thank you, Mike. You said that people aren't ready yet for that.
People aren't ready.
People are not ready yet, right, on the adoption side. So how do you foresee adoption happening? Who needs to trigger whom for this thing to fly, basically?
There are a number of steps. One is the availability of the chips. They're becoming widely available now in the cloud. And so you can go to AWS now, you can go to Azure now, Google is a little way behind, Equinix, bunch of people. You can buy the stuff, you can buy these chips off the shelf. It's just standard EPIC chips and whichever, and Xeon chips. So that's one. Secondly, there needs to be a number of ways to make it easy to use this stuff. As I said, it's quite complex. You don't want to just be taking a couple of memory pages in a vCPU and doing all the stuff yourself. So there needs to be projects, hopefully open source projects, and more of the projects are going open source, I'm pleased to say. More of the products are going open source to support this. The regulators are beginning to pay attention, but regulators can't say anything until there's commercial availability, because otherwise the industry will just push back. But they are beginning to pay attention. And not recession, because it's very difficult to convince people to do new stuff when they're trying to keep their existing businesses going and keep their existing staff, frankly. So that's where we had problems, frankly. One more, I think. Oh, two more. See if we can get through them.
Maybe I have time for one.
Is there any possibility of making it work with accelerators? Or like GPU compute?
That's a lovely question. So the answer is yes. Okay, a bit more than that. So the GPUs are coming. We know there have been some announcements. We expect to see DPUs and stuff as well. The problem ends up being not so much putting stuff on them as creating the trust relationships between the different parties. So there's work going on in the PCIe, I think IEEE, working group at the moment on how that sort of stuff happens. Really interesting, difficult stuff. So the answer is yes, we expect it to come. Try a quick one, if we can, with this gentleman here.
Yeah, so quick one. Is that a theoretical scenario or is a real threat? I mean, is there any real attack happening on that area? Because maybe what you need to get more attention is a real attack, a real exploit that will make the news, for example.
Yeah, the problem is that most of the breaches we've seen over the past 5 years would have been significantly mitigated if this had been in place. That's not enough. It's not enough. People are just finding other ways around it, or keeping stuff in house, or just keeping stum, keeping quiet. So that's why the regulators need to step in. Right, thank you very much indeed for your time and attention, ladies and gentlemen, boys and girls, and everyone online as well. Do get in touch. I'll be around for questions. Thank you.